Alright, so we did our project on the trailer hitch pin. I'm Chris Carlton.
I'm Isidro Guzman.
Cameron Wilson.
Yanni Ritzes. And we gotta click the next slide, you know what I'm saying?
Alright, so as you can see, this is the trailer hitch pin with the retaining pin. It connects the hitch to the receiver, and it is a very vital component. Therefore, it is made with immense strength due to the material. To do this project, we did a couple of different approaches. We did calculations by hand, we did calculations in MATLAB to confirm, and then we did SolidWorks simulations on top of that.
As far as the functions of each component, there are 6 total components in our assembly. They consist of the pin, the retaining pin, the hitch, the ball, the nut, and the washer. The primary function of the pin is to keep the receiver locked onto the trailer, so that's the most important part of this whole assembly. The retaining pin just acts like a shoulder against friction, doesn't really play that much of a big part. The whole hitch is a primary means of lift, as well as the drop-in height between the trailer and the hitch. And the washer is just in charge of distributing pressure evenly between the nut and hitch, so there's no separation. As far as the material selection, we chose steel because it's easy to manufacture, it's cheap, and it's strong. You could use aluminum for the weight difference, but weight is not a big design factor for this assembly, so we went with steel. As far as economic safety and manufacturability, the raw material comes from Japan, and the assembly is manufactured here in the United States. You could go out in the store and buy one of these bombas for between $20 and $60. The bomba in particular that we chose is a class 3, and it can carry up to 5,000 pounds. And for how it's manufactured, 90% of all the components in the assembly are manufactured using computer numerical computation and robotic welding.
So I was in charge of the design considerations. We did 3 different design considerations. The first one is enlarging the diameter of the hitch pin. We decided to knock this one just because increasing the diameter doesn't really change how much the hitch can withstand. Our hitch pin itself is pretty strong, so just increasing it would be pretty redundant. The second design consideration was the 5th wheel hitch, which is similar to the gooseneck. The difference is it requires a large assembly in the bed of the truck. We decided to knock this one just because the amount of space that the 5th wheel hitch takes up in the bed of the truck is pretty large. The last consideration was to change from stainless steel to the aluminum alloy 7075 T4, which has a higher tensile strength and yield strength. The drawbacks is the manufacturing, the cost of manufacturing is a lot higher, meaning these parts would cost a lot more.
So for the static and fatigue analysis, we wanted to calculate several values, and our first value we calculated with our 0.6 inch diameter is our design factor of safety, which we hand calculated to be about 2.36. And then using a standard size diameter of 0.625, we calculated a factor of safety to be about 2.67, which is about what we were expecting to see. And we wanted to see what the factor of safety is for infinite life, and we got about 2.29, which is really good. And we want to see how many cycles would it take for this pin to fail. And we got a value of 7.525 times 10 to the 11. And I'm hoping probably no one has ever used a trailer that many times, so the pin will probably be lasting forever. And we want to see what the max force would be for the pin to fail after 1 cycle, and we got about 8,000 kips, which is about 4 tons of force. So deformation is an active distortion in a shape or object. Due to how close the receiver and the hitch is, there is not much room for the pin to deform. So if there were to fail, it would happen in an instant fracture and not after a slow deformation and then a fracture. So the first thing we want to do is we researched and we found we wanted to use about 0.6 inch diameter, which is about the average diameter size that most pins are. And then we hand calculated the values that you saw on the previous slide. Then we wanted to confirm those calculations, so we went to MATLAB, and the only number that was a little off was the number of cycles till failure, and that was only about 1.6% difference though, so we didn't really, it was just decimal errors. And then the third thing we did, we went to SolidWorks. We made our trailer hitch pin and clip and our receiver, They constructed several simulations such as static, fatigue, factor safety, von Mises, normal stress, and we saw what would happen through all those simulations. And lastly, we constructed our report and analyzed it to make sure everything ran smoothly.
So here you can see the assembly we designed in SolidWorks. On the left, we have the hitch, the receiver, everything in there. On the top right is the retaining, or the trailer hitch pin, and on the bottom right is the retaining pin that goes in there to ensure it doesn't slide out. Here's one of the simulations. We did the von Mises stress on the whole assembly, and as you can see, the trailer hitch pin doesn't feel so much stress. It is more felt in the ball as well as the hitch, as you can see as the colors indicate. Here we did some more simulations. The first one we did was on normal stress. This was just on the pin itself, and as you can see, the stresses is mainly on the hitch. And on the right you have another simulation we did, which is the factor of safety. And the lowest factor of safety is on the left right there where the trailer hitch pin meets the receiver and the hitch. And then the highest would obviously be at the far right where there is no contact. This is the last simulation we did. It's a von Mises of just the trailer hitch pin, and as you can see, the colors distribute the stresses and which ones have greater values and which ones are least.
We also did some design improvements. There are 3 particular design improvements that we considered. The first one was taking the trailer hitch pin or trailer hitch and attaching it to the entire frame of the vehicle. By doing so, it distributes the towing force more evenly throughout the vehicle. It allows it to be distributed evenly. Therefore, when you're taking wide turns and things of that nature, everything isn't focused on one side; it's more balanced. The second improvement included a magnetic cylindrical component that sat on top of the ball mount, which actually helps the tongue and the ball mount be more secure. We decided to take that design a little further. Instead of putting the magnet on top, we decided to put it right below the ball mount around the neck area, just so that it would increase the shear strength of it, as well as do what its original function was, which is to help align the tongue and the ball mount. The last improvement was to consider the gooseneck hitch, which is similar to the fifth wheel hitch, but the difference is in this assembly, it's just the ball mount that lays in the bed of the truck. This allows for better maneuverability, as well as it decreases the sway of the trailer behind going at high speeds and everything like that. It allows the trailer to take easier turns and everything like that, more efficient turns. Yeah.
So what we concluded was that through all these simulations that the hitch would actually fail before the pin due to the strength and the factor of safety of the pin. There was minimal deformation because there was such a small gap between the hitch and the receiver that the pin had really no room to deform if any forces were to enact on it. And we had to conclude that we had a high factor of safety, which we expected, and we wanted to make sure we analyzed and saw how that factor of safety affected the hitch and the receiver.
To add one thing, the force to fail, the trailer hitch pin was 8 kips, or about 8,000 pounds, not 8,000 kips, which may have been mentioned earlier.
This is how the time was allotted throughout the design. As you can see, it's pretty straightforward. Project selection, brainstorming, report, presentation, SolidWorks, etc. Are there any questions?
Yes, I had a question.
What's
Yes.
your question, sir?
Where would you buy one of these things at?
You can find these anywhere.
Hardware stores,
Walmart,
Home
Depot, Lowe's, really anywhere.
Is this something that I would mount in the front of the vehicle or under the hood? Where does this go?
This actually goes in the back of the vehicle, at the lower end of usually trucks, but you would mostly see them on.
Any other questions?
Any other questions?
You over there? Oh, you're scratching your head. Okay.
Thank you. What are we at?
Oh, I forgot to put the
So for the static design factor and factor of safety, right? So we need to find our area, which we did with pi over 4 d squared, and then we have our force at 2 kips. So for sigma x, we use the 32 times the moment over pi d cubed, and to plug in our diameter of 0.6, we get a bending stress of about 18 kips per inch squared. Now to find our design factor of safety, we plugged in our yield strength of 42.35, which we found from this. We're using stainless steel, and we plug that in and we get design factor of 2.36. Now to find our actual factor of safety, we need to find a preferred size, which is, we use 5/8, which is the next size up of 0.625 inches. We do the same thing for the bending stress, and we get 15.854 kips per inch squared. And we plug that back into the same equation, and we get a factor of safety of 2.67. The next thing we wanted to find is what would be the factor of safety of infinite life, which is N equals SC over sigma, right? So we need to find the endurance strength by using this equation with our Marin numbers. So SC prime is equal to half of the ultimate strength, which is 0.5 times 99.35, which equals to 49.675. Then we need to find our Ka, which is a given equation on our equation sheet, and we get 0.798. For Kb, we need to find our minimum number of these two equations, so we're going to use 1.034. And since it's not rotating, we use the equation dE equals 0.37 times d, which 0.37 times d equals 0.222. And then since it's only bending, our Kc is equal to 1. So our endurance strength is now equal to Ka times Kb times Kc times our half of our ultimate strength, which is equal to 40.988. Plug it back into the equation, and we get an infinite life factor of safety of 2.29. So we wanted to see the number of cycles till failure. So we have our equation of N equals sigma over A to the 1 over B. So we needed to find our A, which we got to be about 140.87 kpsi. And then our F is 0.842 from our charts. And then our SC is only half of 99.35, which is 49.675. And we find our B with this equation, and we get negative 0.0754. So the number of cycles it will take till failure is 7.525 times 10 to the 11 cycles. And also we wanted to find how much force it would be needed in order to break the pin on one cycle. So going back through our equation of N, we know that for N to equal 1, sigma rev has to equal A. So sigma, we assume that sigma is equal to 140.87, which is what A equals to. We plug that back into this equation. Your moment is equal to force times distance, which is F times 0.375. We plug that back in, we solve for F, and it would take 8 kips after one cycle to break the pin. And these are just singularity functions for deflection.
Solid. Alright, so as you can see, if you pull right here, the only thing that's stopping is going to be this hitch pin. Here's the safety pin. If you disengage that, pull it out, you get the whole frame out of there. Let's go ahead and put it back in. There we go. Now give it a pull, Chris. Let's see if you can.
I don't think
Nope. Did it have it? Cedro? Try it out, man.
It's not coming out of there. You don't think so?
Get that on there.
nope, it's not coming off.
Cam, you think you got it? It's pretty swole. I think you got it, dude. Get it on nice. Might move the whole truck, but
Nah, I think it's
get
good.
it?
I think it's good.
I think it's pretty safe, I would say. It's looking good. Yeah, buddy. You UTSA.
Go ahead.